It is such a pleasure to be with you all here today. I'm going to get started. Today, we are going to be talking about the National Aeronautics and Space Administration engineering to benefit life on Earth. Okay, the first thing I want to talk to you about, this is just my own personal slide on helping you to decide now to make some important choices in your youth that are going to benefit you throughout your life. And I'm sure you've heard these things before, but I want to make sure I emphasize these tonight. Be a good person. No matter what you do in life, you need to personally decide that I'm going to be a good person. Be trustworthy, work hard, be respectful of others, obedient to your parents and to your leaders, and then help other people. When you do your studying, study to learn and to understand. That means you might need to do a little bit more homework than what's even required or asked of you of your instructors. This is not just for high school, this is also for college. We want to make sure you are understanding why you're learning what you're learning and how it's going to apply in life. Being curious and creative, expand your thinking, ask questions, always ask questions, and use your creativity. Think out of the box. I'm sure you've heard that phrase before, but that is what's going to help set you apart from other people. When you can be creative and curious and asking questions, you will be able to expand or raise your level of thinking above that of someone else's. Develop all the talents and skills you possibly can while in your youth. Join sports, be in clubs, be in band, choir, take on those leadership positions. And here's me when I was in junior high playing basketball, and I was a cheerleader in high school, and I graduated. So you can do it. You can be in extracurricular activities and develop your sports. You can also develop your mind, and you can do it all. Some of the top 3 things that employers are looking for, so always keep this in mind. Can I solve problems? They're looking for people who can actually solve problems. Are you an effective communicator? Can you write well? Can you speak well? It is so important to be able to express your ideas. And then absolutely must get along with other people. You can see in the work that I do at NASA, we do it in teams. We have to be able to work with people of all different races and backgrounds. And also as a mission leader, I have to work with hundreds of missionaries. And so it's very important that we learn good skills to get along with other people. And by doing these things in high school, developing your talents and being in clubs, taking on those leadership roles, that's going to help you to learn how to get with other people. So NASA stands for National Aeronautics and Space Administration. What do we do? Why do NASA explore? Our purpose is to discover new worlds. This photo behind you shows the Saturn V moons. So we are constantly sending spacecraft out into the solar system to explore or to discover new worlds. We also, in the process of doing all of this work, we explore the unknown. It's not just in space, but also in Earth, observing the Earth. Anything that we do, we create, we innovate, we engineer to benefit humans. Our purpose is to benefit human life on the Earth. And you're going to see some of that throughout this presentation. So let's begin with the end in mind. These are some of NASA's successes that we've had. NASA engineering to benefit life on Earth. We have mission success through imagination, engineering, and collaboration. So you need to be creative and imaginative. You also need to learn the sciences and the physics and the math and the computer science and the software engineering. And the collaboration, because you're going to be working with so many different people in the work that you do, we have to be able to get along well with others. And so these are some of the extraordinary things that NASA has done using all of these characteristics. The way NASA accomplishes these missions is through system engineering. Now, system engineering is an art and science of developing an operable system that meets requirements within imposed constraints. Those constraints can be cost, schedule, and also performance. It incorporates balancing all the different disciplines. It could be your mechanical, your electrical, your software. We put all these disciplines together. We also look at the systems, and we have to perform trade-offs and compromises, because sometimes the technology we want to use in a system is not available. And there's also some commercial items that we can use to help us with designing our systems. So we use those as trade-offs. Requirements come from the customers. So NASA's customer is the federal government. So we work for Congress. So Congress gives us our requirements and our mandates. They tell us to go to Mars. They tell us to discover the solar system. They tell us to build new rockets. And so we answer to the United States Congress. Also, system engineering puts all these individual systems together to make subsystems. And so each of these subsystems have to interface. And that's what we do with system engineering. This is the methodology that we use to develop these complex systems. Now, the art of system engineering is technical leadership. So here is your leadership. Leadership is making sure that the system's technical design and the integrity are maintained throughout the entire project, from the start of the project till the closure of the project. The system engineering is balancing, it's pulling in all of your engineering instincts, your creativity, your broad technical domain knowledge, your communication skills, your problem solving, and also your leadership skills. Now, when a project, we look at the complexity of the project, the size of the project, and the constraints of those projects. And that determines the level of system engineering you will use. So if your project is not a large project, maybe it's just designing something for a part of the center that you're going to work for, then you wouldn't need to use, you would tailor your system engineering processes. But when you're building something huge, like the International Space Station, you will have a system engineer over the entire project, and each of those subsystems, mechanical, electrical, maybe the solar arrays, all of those different systems will have their own system engineer. The leadership skills are just as important as the technical skills. So it's important for you to have both. Now, the science of system engineering is systems management. And this is using a systematic, disciplined engineering approach. And this approach is quantifiable, it's recursive, it's repetitive, and it's demonstrable. So it's about the organization having all the right training their people, having the processes in place, and continuously being persistent in making sure that people are following the system engineering processes. Now, systems management applies throughout the life cycle of the project, with developing, operating, and maintaining the integrated system throughout the project life cycle. And since projects can last for 10, 20 years, it's very important that you document your work so that, again, we can repeat this design if we ever need to repeat the design. The characteristics of a good system engineer. So you can check yourself and see, am I intellectually curious? We talked about curiosity and how important it is. This is a main characteristics of a system engineer. Your ability also to make system-wide connections, taking each individual system of a large project and being able to see the whole project and how they all work together. You need to be a strong member of the team. So you've got to be able to work with others. Comfortable with uncertainty and the unknowns. And then there's this thing called proper paranoia. We can maintain our paranoia by looking at the risk. There's always going to be some likelihood of something happening, And then also, what's the impact of that idea or that incident or event occurring? This is where we look at risk. You need to be self-confident and be able to make decisions throughout the project, but you need to leave the egos at the door. That's one of the things we say a lot in our meetings at NASA. Check the egos at the door, because it takes teamwork in order to be successful. We also have processes, but you can tailor those processes. And so a good system engineer knows when to stop the process and when to move on. We have diverse technical skills to apply sound technical judgment. That means my background is electrical, so I would be providing electrical expertise on a different project. But you also need to pull in some of the mechanical and maybe some of the fluids technology, your physics, and you work with all of those in order to have a project that's successful. You have to be comfortable with change. Sometimes your budgets might get cut. The pandemic we just had with the COVID virus, those things will slow you down and they will change what you have to do. And so you can't just panic because of those things. You have to think logically through to figure out, how will I proceed even though we have change. Exceptional two-way communication, being able to communicate your skills and your ideas, and also being able to write them, and the ability to see the big picture, yet you can work down into the levels of the details. These are just a few of the characteristics of a good systems engineer, and we work on these all the time. So you don't have to have all of them right now, just be able to have most of them and see that that's something you want to do. This is NASA's systems engineering engine. And it just shows how we start with requirements under the systems design process. With a requirement, you can design a system. Your system has to meet all the requirements that you get. Then you come across onto the other side, you start developing your products. Your products have to meet those requirements. You verify and validate that the products have been designed right and correctly. And then you have your product and you transition it to your customer. We deliver our spacecraft, we deliver rockets to the United States Congress, and we say, this is a NASA product. We are doing the things that you have asked us to do. In the middle is where you have all your technical management processes. This is part of your documentation, your drawings, all of the software that you're using in your projects. You have to document these things so that you can reproduce this work if you ever needed to reproduce it again. Throughout the life cycle of the project, you have to maintain these. So this is just an overview of the life cycle of a project. You start with concepts and requirements. This is where your creative thinking is going to come from. Trade studies are also a part of the beginning phases of a project. Then you have an idea of what you want to do. And so you start creating simulations using software or engineering models. And some people can build tangible things like prototypes. And then you're finalizing your design. After the design is finalized, you have to fabricate and build it, put it all together. And this is when you start developing your test procedures and your requirements. And you start with your system level testing. And then each system has to communicate with other systems. So you have to do system integration. And then you verify your requirements. Did I build the right system? Does the system perform all the operations that the customer is expecting? And then the fun thing is, now your system is operational. You have used your system engineering methodology to develop an operating system. And so the system is operating, and then you have to maintain it. And it goes throughout its life cycle. Remember, that could be for 1 year, 2 years, 3 years, or 20 years, or 30 years. And then you close out the project by doing up your final documentation. This is just a V model of what I just explained to you. Many companies, or you may be able to see this in the future, it just starts off with your concept designs, going through requirements, doing your high-level design, your detailed designs of all your different subsystems. Then you manufacture. Then you come up on the other side, you start testing in the individual systems, and then you have integrated testing. You verify and validate that the system performs everything you did, and then you now have an operable system. In the middle, it shows the documentation that you're updating and modifying throughout this process so that you can have a repeatable system. Now let's get into the projects, showing you the application of systems engineering. The first is an autonomous flight safety system project. Here, your collaborations, you have to work with other people. This was a project that was collaborations between NASA, the Air Force Range Safety Department, and the Defense Advanced Research Projects Agency. So we all sat together and we had the problem was the ground infrastructure for radars were getting old and they were very costly. And we used these radars to track the rockets as they cross the horizon into space. Well, we had to come up with some concepts. We thought, why don't we use advanced space-based range concepts using global positioning satellites and sensors and inertia measuring units, along with some software, and put all that together. And we could use that, we could put it on the rockets so that as the rockets cross the boundaries or as they are violating flight rules that the range safety officer would implement, this particular device would then terminate that rocket or shut it down. So the requirements were, let's develop a self-contained range safety system that's mounted on a launch vehicle. And this system will implement flight termination rules. We will either shut the engines down or we will destroy the rocket if it looks like that rocket is not going to reach space altitude or the speed, or if it looks like it's not going to reach its destination. And we would do this without using the ground infrastructure radars or the range safety officer. It was a big idea. Let me tell you, it worked. It happened. Here is the testing. This is individual. We did system testing. We put our navigation sensors and this software with the navigation sensors and the inertial measuring units on flight on a fighter jet, an F-104 fighter jet. And we asked the pilot, we actually paid him to fly and do barrel rolls and do some Mach speeds to try to break the connection with the GPS sensors. We needed to test those sensors to make sure they wouldn't lose the rocket. Once we proved that that software was working on the fighter jets, we actually put it in a relevant environment on a sounding rocket at Wallops. And so Wallops tested it out. Our final integration testing occurred on a SpaceX Falcon 1 rocket out in Kwajalein Island. And you can see over here, Kwajalein is way out in the middle of the Pacific. So if anything happened with these test flights, it was not going to hurt the public or harm any of our equipment or the public. So what were the results of our engineering? The innovation that benefits life is now, NASA has developed an autonomous flight safety system software. It was licensed to a commercial industry and the name has changed to Autonomous Flight Termination Unit. The AFTU technology has been modified by SpaceX and utilized on their SpaceX rockets that launched from the Cape Canaveral Air Force Station. So their first launch of using the AFTS, and remember this is now, we're no longer using the ground infrastructure radars. We're using GPS sensors and satellites to track the rockets. This is so advanced, it is so new. So SpaceX, this was a first demonstration flight, took place in February 19 of 27 on a mission that they were going to the International Space Station. It was so exciting to hear that the AFTU unit was working and it was a go for launch. On July 10th in 2017, the Senate Committee on Armed Services created a directive to the Secretary of the Air Force to provide a report to various government agencies on a strategy to transition the autonomous flight safety system and the termination systems on the eastern and the western ranges. So now by 2022, if any rockets are going to be launching from the East Coast or the West Coast, they must have an AFTU on board. General Brigadier Wayne Monteith was interviewed by Florida Today, and he named this a game changer. He said it had demonstrated technology that would improve safety, it would improve lower costs, and enable more launches from the Eastern Range. And he said it was tested extensively and is actually safer than having an individual in the loop perform this range safety operations. It's a fundamental game change, changing the way we do business. So now we are entering into the Artemis program. During the Apollo days, we placed 12 astronauts on the moon. Your generation of a lunar exploration program is called Artemis. Artemis is NASA's humanity's return to the moon. I was privileged to work on the Artemis launch release subsystem at the Kennedy Space Center. I was the project manager that led the team of engineers that developed the launch release system. Now, this was a collaboration. Here again, you're going to be working with different people. Kennedy Space Center, Marshall Space Flight Center is in Alabama, and then we had contractor engineers to help with this design. Artemis is NASA's Lunar Exploration Program to return humans to the moon that will prepare to propel us to Mars. So we're going to the moon first and then to Mars. And this is I'm so excited about this program because the first woman and the next man will step on the moon by 2024. So it's women, girl power. The Space Launch System will be the rocket that will be the most powerful rocket in the world, and with the capability to launch humans beyond Earth's orbit. This is the Block 1 configuration. It will have 8.8 million pounds of thrust. That's 15% more than the Saturn V rocket. Now, the launch release subsystem generates the T-0 for this launch, and it also uses that signal to separate the umbilicals. You can see all of these umbilicals that are connected to the rocket. Well, we generate T-0 that will separate those umbilicals, and they'll fall back and lock into place so that they won't have any connections with the rocket. The LRS system also had the requirement to burn off any excess hydrogen from the vehicle's core stage engine. So that's down here. While we were in the process of coming up with our concept designs and doing our trade-offs, we discovered that the pyrotechnic initiator circuit boards that provide this critical safety signal to ignite those hydrogen burn-off igniters, to burn off that excess core engines, that those boards that we had used during the shuttle program, we couldn't use during the new Artemis program. The board designs were old and the components were not going to last for the next 20 years. That was a part of our requirement. Everything we designed needed to last for 20 years. So we did trade studies and we looked at commercial off-the-shelf equipment that could possibly help us with this. And none of them seemed to be able to meet all the requirements. So we got chief engineer's approval to design a new in-house design for the pyro initiator circuit boards. These boards ignite these pyros. You've probably seen this before. You will see these sparks that fly. They're actually absorbing, they're burning off the excess hydrogen that comes out of those engines. If that hydrogen oxidizes in the oxygen in the atmosphere, it can cause an explosion on the launch pad. And so it's very critical that we absorb all that excess hydrogen that could be leaking out of those engines while it's sitting on the pad. Here's a video. In about T-10 seconds, the hydrogen burn off igniters, those are sparks, they start to burn off the excess hydrogen, and then this is the space shuttle can launch. And this will also occur for the Space Launch System. I'll show it to you again. T-12, The H buoys fire, they're burning off the excess hydrogen, and then the rocket can lift off safely. Okay, so we also did integration testing with the launch release subsystem. This picture here shows our test setup for the integration testing. This part of the testing was the Space Launch System rocket simulator. The umbilical connects to the rocket. These umbilicals for the Orion service module. The Orion service modules where the astronauts are going to be living, or inside of the rocket. They ride in the Orion service module. So they need clean air, and they also need electricity and fuel into that component. So this would be the LRS system would then send the release signals to this umbilical. And then the umbilical is connected to the mobile launcher simulator. So we needed each of these is system engineering, combining integrated testing, showing 3 different systems, actually 4. You have the rocket, you have the launch release system, you have the umbilicals, and you also have the mobile launcher, which is the large tower that the umbilicals are connected to. So this is integrated testing. These umbilicals provide the power, they provide communications, commands, and controls, coolants, and the fuel to the rocket and to the spacecraft. And I was able to support the launch release subsystem on a cross-program launch separation action team, where with my system engineer, we looked at the critical timing of this, which we came to only 6 seconds. We only had 6 seconds to provide that launch release signal, release these umbilicals, and the umbilicals had to fall back and lock into place. And at T-0, then you count up to 6 seconds. That was all the time we had to get out of the way of the rocket to make sure we wouldn't have any reconnect with the rocket. So this umbilical testing was done at the Kennedy Space Center. And what was the benefits? The launch release subsystem enables safe human spaceflight of the Space Launch System rocket and the Orion spacecraft. We were able to release all of the umbilicals and also burn off the excess hydrogen underneath those engines. And this is the mobile launcher platform. You are looking at the tower where the new space rocket will be attached to, and you can see the actual umbilicals as they have been installed on the mobile launcher. You're getting to see it before it happens. Now, one of my last projects I worked on at NASA was the Mars 2020 Perseverance Project. And so we're going to see some of these wonderful slides here. Where are we in the solar system? I want you to gain an appreciation for NASA spacecraft. We have beautiful photos of all the planets in our solar system because of NASA spacecraft. When you look at Jupiter and you see the size of the Earth compared to Jupiter, and you see Saturn's beautiful rings, and you see a beautiful Neptune and Uranus, and Mercury and Venus, we have these photos because spacecraft have flown, NASA developed spacecraft have flown throughout our solar system and are helping us to understand what it is like on the environment of these planets. We now have a spacecraft headed to the sun. It's called the Solar Parker Array. It's going to be able to give us more information about our sun than we've ever had before. So it's just going to be wonderful. So let's zoom in on 2 of these planets, Earth and Mars. Mars is the most Earth-like planet of all the planets. That's why we want to go there, to see maybe we can learn what happened to Mars could happen to Earth. Mars is about half the size of Earth. And why is that? Because Mars doesn't have any flowing water or oceans on it. We have discovered frozen water. They do have ice on the North and the South Pole. We know that Mars is about, the average distance from the Earth is 100 million miles. I don't even know how to compare that, what to compare that to. That's pretty far. Mars atmosphere is poisonous to humans. So we can't send astronauts there until we figure out the right kind of suits and how to keep them alive. The atmosphere there is about 90% carbon dioxide. Mars' atmosphere is also very cold. In the daytime, it's about minus 81 degrees Fahrenheit. At night, it can get over minus 100 degrees. The planet is dead because the iron in the soil is rusted. It has already oxidized. We also know there's no protection from the sun's radiation on Mars. The Earth has an electromagnetic field, and our atmosphere protects us from that radiation from the sun. Mars no longer has that protection, and so if you were to go there, your radiation would be a problem. The gravity on Mars is about 40% of Earth's gravity, so you're gonna weigh a little bit lighter. So if you're about 120 pounds on Earth, you would be about 48 pounds on Mars. Scientists from around the world took 5 years of research to decide which location on Mars they would send for the Mars 2020 rover. This particular mission was to seek for new signs of microbial life. And so they selected the Jezero crater. This crater was selected because we believe it was once home of a river delta. Imagine water on Mars if it was flowing water. So this would have been a good place for microbial life. And so if we can get some samples of the soils and the rocks here, they could be filled with Martian minerals and give us some idea if there was ever any signs of life. So that's the background. That's the science of why we are going to Mars. I was privileged to leave Florida, Kennedy Space Center, and fly all the way to California and live there for almost a year, working with the Mars 2020 team, helping do verification and validation, which is systems engineering, on the Mars 2020 rover. Just as a simplest form as I can say, engineering, the engineers create and they build the rover. We had to work with scientists who came up with the rock, the exploration of the rocks on Mars. And so they're also the people that are discovering. And so if you want to be an engineer and help build the spacecraft, I applaud you. If you want to be the scientist that helps analyze the soil and discover whether or not there's life or have there ever been life on Mars, to help us to learn about what could possibly occur on the Earth, I applaud you. Both are needed, and both will work together in the Mars 2020 Perseverance Project. These are 2,000 engineers and scientists at the Jet Propulsion Lab that worked on this project, but they're not all. In all, there's probably about 5,000 people that helped make this mission successful. Again, I cannot emphasize the importance of getting along well with other people and being able to work in teams. This particular project took 11 years to complete. So you definitely need to document it because the people come and go, and they may not be around towards the end of the project. The cost was about $3 to $5 billion. You need money to build the rover. You need money to pay for all these engineers and the scientists. You have international collaborations. You have to launch the rover. You have to pay for the launch team. And then now the rover is on Mars performing mission operations. And if you haven't found me yet, that's Sister Amos. This was our requirements. Remember, if you remember the system engineering process, requirements is at the very beginning, concepts and requirements. And the requirements come from Congress for us. So they asked us to build another rover, the Mars 2020 rover, and to seek for signs of life. We're looking for microbial life, not like an insect or an actual human being or a skeleton. We're just looking for any signs that there possibly could have been life on Mars. They're going to collect rocks and soil samples. So that was a part of the mission. We had to have instruments that could do that. Understand the habitability of Mars so that one day we could send humans to the planet, and then demonstrate some technology for future explorations. That's where the helicopter came into place. And also there's an experiment that you'll see called MOXIE, which will extract some oxygen out of the carbon dioxide atmosphere on Mars. So we landed on Jezero Crater. We designed the rover. We launched the rover on July 30th from Kennedy Space Center. It took 7 months to cruise space to get to the planet. It traveled almost 300 million miles to get to Mars, it's Jezero crater. And then it landed on Mars. We've done that on February 18th, and now we are doing operations on the planet. This slide just helps you to see our requirement was to operate on Mars for 1 Martian year. And 1 Martian year is about almost 2 years on the Earth. So that would mean this system needs to be operational until about January 6th of 2023. 1 day on the Earth is 24 hours. On Mars, it's 40 minutes longer. So we can't call it a Martian day, we call it a sol. So if you ever wondered why they refer to sols, then that's what it's referred to as. This video shows the Earth and Mars orbiting the Earth. You can see the Earth will go around twice, 2 times, almost 2 times before the Mars orbit will go around the sun only about 1 time. The ideal time for launching our spacecraft of the 2020 rover is when these planets line up. That would be the shortest time to allow them to catch up. So when Earth and Mars line up about right now, this is when we would launch. And that time frame would give us about, we only had 2 months window to launch. So the time frame was July and August. And so if we had missed that launch window, here again is critical schedule. If we had missed that launch window, we would have to wait another 26 months to try and launch that spacecraft again. So it's very important that we met our deadline. This is the Mars 2020 Perseverance rover. You can see all the instruments. There's 7 new instruments. It's pretty cool. The size of the rover is about the size of a Mini Cooper, and it weighs about 2,260 pounds. There's 23 cameras on this rover. So we were able to see the actual landing and views of the spacecraft while it was landing on Mars. And now you can see all types of photos. They use different Mars. Some use laser technology, some are using UV, and some are using different technologies to analyze, X-ray technologies to analyze the rocks and the soils. And you can also see that we have different flags here, not just the United States. We had France and Spain, and I think that's Norway, that was helping us on some of these experiments. This particular rover is the first time we have microphones, so you can actually hear the sounds of the rocks crushing or the wind blowing on Mars. And of course, we talked about the helicopter demonstration flight. This was testing, integration testing. Here we were testing the robotic arm with all of the different software, the mechanical and power, all those different subsystems coming together in an integrated test. And let's see if we can get this video to work. This is the robotic arm doing its maneuvers, and it does all of this autonomously with software on board the rover because there's no people there to tell it what to do. The software tells it exactly what to do. On the end of that robotic arm is a drill, and that drill, there's about 7 different size of drills on there, so they can drill into harder, different rocks. They can core off the top of the rock, and they can drill deep down into to store these samples. A part of our mission was to collect soil and rock samples. So there's a sample and caching system, and it's going to collect these samples into tubes, into titanium tubes, and they're dropping them all over the Jezero crater. And we have another mission coming up that will go and retrieve those samples. Another requirement, which we found out from previous rovers, was we couldn't use solar systems. So we had to come up with another idea for the power on this rover. The solar power would, we had some dust storms on Mars covering up the solar panels. And so that was preventing the power from operating, and it shut down the Opportunity rover. So we had to discover a new way of providing that power. So we use a nuclear power source. We call it a multi-mission radioisotope thermoelectric generator. At NASA, we don't call it that long word. We use a lot of acronyms. We refer to it as an RTG. So it's nuclear power physics, and it's generates a lot of heat. We convert that heat to electrical power, and that electrical power powers all those cameras, microphones, and instruments on board the rover. The amount of power it produces is about 110 watts. That's about as much power as a light bulb. So that's all it takes to run those instruments on the rover. And because of the plutonium and the skills required, this particular RTG cost $75 million. I was able to look at a lot of assembly and integration and the installations of the components. So I took these photos so that you could see them. You can also see the helicopter at the bottom. That's the actual helicopter or drone, if you want to refer to it as a drone, but we call it a helicopter. The rover here you can see in one view, the wheels are kind of up. That's the stow position. That's the position it flew all of those 7 months to get to Mars. And the technicians and engineers there are installed different parts of the instruments on the rover. The helicopter was installed underneath the belly of the rover. I believe that's what's coming up. Okay, I was able to support 2 main system tests. System test 1 was cruise, entry, descent, and landing gear. So we were able to test this out. And the time frame was about a year before launch. So we had already tested entry, descent, and landing 1 year before the rover actually cruised and landed on Mars. We also tested the first 3 days of first 40 souls on Mars, doing the power up operations for all the instruments. This is our team. We are in the assembly, test, launch, and operations facility. We are in the room behind the rover. We are using we're using the final flight software to test out the rover, which is on the other side of these walls. Only people with special training are allowed to be in there with the rover. That's due to planetary protection. They're fully geared in the white clothing, their hats, their faces, everything is covered so that they're not leaving any types of fabrics or sheddings onto the rover. And no one is allowed in there to make sure that we don't take samples of the Earth onto the rover and claim them as life on Mars when they actually came from Earth. These are 2 important test chambers. This is integration testing in the relevant environment. The rover launches on a rocket. So you have to do acoustic testing to make sure that it can withstand the vibrations of the launch rocket. The other test is in a thermal vacuum chamber. Here, we can simulate the Martian environment, those cold temperatures, the low gravity, the no atmosphere, very little atmosphere, and to make sure that the components and everything would work properly once it entered into the Martian atmosphere. The Mars 2020 rover launched from the Kennedy Space Center at the Cape Canaveral Air Force Station on an Atlas V 541 rocket. You can see on these views that the fairing, the very top of the rocket, is where the spacecraft resides. And then once it reaches into space at the right speed, it propels the spacecraft and it travels about 13,000 miles per hour in a vacuum of space for 7 months. And that's because the Atlas rocket had that capability of putting it at the right altitude into space and also giving it the speed it needed to reach Mars. This Atlas rocket weighs about, fully fueled, is 1.17 million pounds. Half the rocket weight is fuel. So we definitely need to come up with better ways of how to overcome gravity. This is an expendable launch vehicle. It can only be used once. So parts of this rover will be, the launch rocket will be destroyed upon reentry into the Earth's atmosphere, just burn up, or other parts of it will be lost in space. To give you an idea of what is 1,000,000 pounds, it's about lifting 3 whales off the Earth. This is now we've launched, and so now we're entering into the Martian atmosphere. So this photo here shows that we tested this at the Jet Propulsion Lab to make sure that it would work properly. And then here again is this is a graphic depiction of Curiosity's sky crane maneuver. Mars 2020 used the same type of maneuver to land on the surface of Mars, where it lowers it down on 3 main cables. And then you also see a communication cable, that's the wiggly one, where you can share electrical signals, control signals. Just one slide on the helicopter. This little helicopter weighs, it's about the size of a tissue box. It weighs 4 pounds on Earth, so we know on Mars it's a lot less than that. It was probably about 1.5 pounds on Mars because of the gravity. And it has completed about 7 test flights. This was a technology demonstration to see if we could actually fly on another planet. And this was the first powered aircraft on another planet. So it was a great technological accomplishment for our country. It has successfully flown 7 different flights. These are not long flights, it's just a demonstration. So the flights are like 30 to 90 seconds long. And the magnificent technical achievement here is that the rotors have to spin almost 5 times the speed of a rotor on the Earth, because Mars it has a very small atmosphere. It has to create its own lift. And so on Earth, helicopters blades spin about 500 RPMs. This helicopter blade spin about 2,500 RPMs to create that lift on the planet. The helicopter is used as surveillance to fly ahead. They can be used for future missions with our astronauts. They can fly ahead of the astronauts and be like scouts to look out for them. They can also fly over craters and take photos and videos in places where the rovers cannot roam. So the innovations and benefits of life on the planet is the Mars 2020 robot will help us to prepare for human explorations. We send robots first before we send humans. We're also being able to learn about the habitability on Mars, the climate, the environment, and what resources are there that we can use. The helicopter technology will be able to support maybe future robotic vehicle flights to explore over craters and again provide that surveillance for human spaceflight. And all the science is just giving us more information to help us to know whether or not there was life on Mars. The last project that I want to talk to you about is Artemis. This is your generation of Lunar Exploration Program. And there's a short video that we're going to show. This will give you an overview of NASA's Artemis program that we are going to the moon by 2024.
50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible.
Very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
And more in testing?
This system is capable of being the catalyst for deep space missions
we need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources,
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity,
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and onto Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going. We're going.
Okay, in the Artemis video that you just saw, we talked about the Gateway. The Gateway is this habitat that's going to orbit the moon. My very last assignment at Kennedy Space Center was developing requirements for the Gateway Logistics Module. I'm so excited to share Artemis with you. This is a collaboration. The Gateway Logistics Module is a collaboration between Johnson Space Center, which is in Houston, Kennedy Space Center, which is in Florida. We have many commercial partners and also international partners, the Canadian Space Agency and the European Space Agency. So Artemis includes the Gateway, and the Gateway is just going to be this small spaceship that orbits the moon. It's going to provide living quarters for astronauts. That's in the middle. The logistics module is more of the round habitat that's on the end. It'll provide all the logistics, the experiments, and the research and science labs for the astronauts to work in. And also the more gold-plated device is going to be the human landing system. This is what's going to transport the astronauts back and forth from the moon, back and forth to the Gateway. And we're hoping to live on the moon for sustained presence for months and even up to a year at times. So the Gateway Logistics Module is going to provide all of the cargo, the elements, and the fuel for the astronauts. And we contracted that work out to SpaceX. So they are now the commercial partner with NASA that's going to build the Gateway Logistics Module. This is the plan for the Artemis Phase 1. Again, I just want to emphasize this is going to be where you all will be able to support instruments and payloads that are working on the moon. Some of you may be involved in this work in your universities, or when you finish college, you can be a part of the Artemis program. Humans will be able to live and work on the moon. We're going to first launch that Orion capsule. It's going to orbit the Earth first. Then there's going to be a mission where it orbits the moon. Then we will start building the gateway, which is with the solar electric propulsion system first. That's what keeps it into orbit. Then we start attaching the logistics module and the habitat module where the astronauts will live. And then finally, we will add the human landing and the gateway will be complete. When that's complete, we will launch humans back to the moon and have sustained operations around 2024. So, how is this innovation benefiting life on Earth? The Artemis program enables sustained human presence on the moon. And so this will help us to have future, once we learn how to live and work on the moon, we can learn how to live and work on Mars. This program fosters partnerships with different companies, commercial companies, and also international partners. And it also establishes new economies, new types of work, new companies, a new space business. And Artemis will inspire you, our next generation, to want to study physics, to want to study math, all of the STEMs, the science, the technology, the engineering, and math, to help us to return humans to the moon and also to Mars. With that, I just want to let you know that we are working on a gateway so that you can have, so that the United States can have sustained presence on the moon to do exploration so that one day we can go to Mars. This is how NASA does system engineering to benefit life on Earth. Mission success through imagination, engineering, and collaboration. Thank you.